Hello, everyone. So I just want to go through a couple more examples of the Lewis structures. I know that they're confusing at first and that there's kind of a lot going on and a lot that we're asking you to do. And I also know I only had a chance to do a couple of examples in class. So I thought it might help some of you who at least kind of have a general idea of how to start to see a couple more examples. This is not as good as the notes that we originally went through. So if you're totally lost, you should go to the notes first. And remember, I presented two methods. And so again, for vast majority of you, I think one of those two methods is the way to go. Especially if you're really, really lost, at least start with one of those two methods. So start trying to make the table, or for the second method, the CCOO, at least start counting up valence electrons. So you can at least give me somewhere to start with. It's just really hard if you are telling me, I don't even know where to start. So at least go back to the notes and look at that as a starting place. And then these, hopefully a couple more examples, will start to solidify what we're asking you to do. I think the last thing to mention is that there's really no one way to do this. The two methods I'm presenting over the years seem to be pretty good for students. It seems to click for students eventually as you practice. But there's really no specific way or set order of things that you have to do. But I think a lot of you just like to be told, here's a method, just do this every time and it works. And that's the case for both of these. But if you get really good or you find something else or another teacher is teaching in a different way, then feel free to do a different method. Ultimately, you need to be able to use, you have to have the correct structure. You've got to get an octet around all the atoms in that structure, unless it's hydrogen, you just need duet, you just need two. And you need to use up all of your valence electrons. If you're able to do that in a different way than I'm presenting, great. But if you just don't know any better, then do one of these two ways. It'll be the best way for me to help you. So the first method I'm going to do is the table method. And for this, I'm going to do PO4 with a 3- charge, which is phosphate. You'll recognize that as a polyatomic ion. As I've mentioned in class, the table method's a little more effort, but it also gives you everything you need. Whereas our other method is a little more guess and check. And so I think you just need to think about what type of learner you are, or maybe just what type of person you are, and when you're trying to decide which of these methods to do. The table method, I think, is the way I would start, especially if you're having trouble. Okay, so your table's always going to have two columns. Now, the number of rows depends on how many elements are in your molecule. So here I've got phosphorus and I've got oxygen. And so I'm only gonna have two rows, one for phosphorus, one for oxygen. So I'm gonna draw those like this. And then we'll total things up on the bottom. So we'll go ahead and put phosphorus here, and I've only got one of phosphorus. So that's what the 1 times means. And then for oxygen, I've got 4. And then finally, the two columns will always be the same. The first one is our octet electron count. And the second is the valence electron count. So again, the table is always going to look like this. You'll always have those two columns. You might have more rows. Like if I had 3 elements as part of this molecule, then I would need 3 rows. All right, so let's start to work with it. The octet column seems a little bit silly to have to do, but there is a reason for doing it. Now remember, octet, the idea is that all atoms want an octet in their outermost energy level. So S2P6 for a total of 8, that makes them very stable. The noble gases already have that configuration, so all the other elements are trying to get towards that. In this case, because we're dealing with a covalent compound, we're going to share electrons to do that. The one exception for the octet electron column, because it's always going to be 8, the exception is hydrogen. So I'm going to put a little star. If hydrogen is involved, you only need 2 valence electrons. So it wants 2, and it's going to be like helium's configuration, and it's content. Otherwise, we're always going to use 8 in this column. So phosphorus, there's only one of them in this molecule, and it wants 8 valence electrons to be stable. So we have 8 coming from that. And then oxygen also wants 8, but there's 4 of them. So all I'm doing is just totaling up how many valence electrons total do we want to get octet. So it's going to be 8, and total 40 electrons. So what that number is telling me is if I had 40 electrons for this molecule, then everyone should be happy. But we don't. And that's the reason bonding has to occur. And so that's what the second column is about. I'm going to use a periodic table. You've been labeling periodic tables. And so hopefully you've got this material already. We're going to count up how many valence electrons for each of those. So looking at phosphorus, look at its position on the periodic table. It's just under nitrogen. And phosphorus has, again, there's only one of them in this molecule, but it's going to contribute 5 valence electrons. So 1 times 5, we have 5. And then oxygen is just 1 over. So that group is going to have 6 valence electrons. Remember, there are 4 oxygen. And there's one more important thing with this specific molecule, this phosphate, is notice that you've got a -3 charge on this group. And what you need to remember is that with a -3 charge, in order to have a negative charge overall, we have to have gained electrons. So this PO4 group, in order to bond correctly, has gained 3 electrons. You need to add 3 electrons to this total for valence. And again, that can be a little bit tricky, but there's kind of a nice trick here. If you were to total up 5 and 24 that were currently there, it gives you 29. And for our first year chemistry course, you should never have an odd number of valence electrons. As you start to think about what we're going to do, we're going to pair them up either in bonds or as separate electrons within the S or the P outermost energy level. So you should never have an odd number. And so that should kind of be an alarm of, well, I'm missing something. You might be missing the -3 charge. So 5 plus 24 gives you that 29, plus the 3, we get our 32 electrons. Okay, so that was part A of this. That's the first step. So part A is simply completing a table. Now part B, think bonding or bonds. So for part B, once we have our table all established and we've completed those 2 columns, now we're able to figure out how many bonds are going to form in this molecule. And again, if that's nice to know ahead of time. If you're doing my other method, the CCOO, you won't know how many bonds until the very end. And so you're going to have to guess and check a little bit to get there. Here, we're going to calculate exactly how many bonds from the start. So I'm simply going to take the difference between these 2 numbers right here. I want 40 electrons to get octet for everyone. However, I only have 32 to work with. So we take the difference, 32 taken away from the 40. So that difference is going to be 8 electrons. Now, there's an important thing here you need to remember, and this is always an issue. Remember that bonds, when you draw a line to represent, so if we're going to bond, hydrogen to fluorine, I would show a bond there, and there's other electrons that are missing. But this single line, that represents 2 valence electrons. So here, if I've got 8 electrons I'm trying to use, but I'm going to turn them into bonds, if I divide by 2 electrons per bond, I know that I've got 4 bonds to place. If you try to end up placing 8 bonds because you forget to divide by 2, it's going to be a mess. And so if you're having trouble and it seems like there's way too many bonds, double check, did you divide by 2 to know that there's 4 bonds to place? Again, each bond can hold 2. So 4 bonds, each holding 2, is the 8 electrons, but you need to just realize you're going to place 4 lines in our final. And then finally, part C is going to be just then how many leftover electrons do I have to place? Now you're always going to place them in pairs. Don't just add single, right? We're always going to pair them up. It has to do with our electron configuration. And the way we're going to get to part C here is that 32 electrons for the valence are all I'm allowed to use. So when this is complete, I'm going to have used 32 electrons exactly. And then all of my atoms will have an octet around them. But I want to know how many leftover electrons that I need to place as dots that are paired up. So I'm going to take away the 8 electrons I already know I'm going to need to use as bonds. So 32 electrons are what I'm allowed to use total. Those are just the valence electrons that all the atoms can contribute. But I need to subtract away the 8 electrons I know are going to be in bonds. And so when I do this, should end up with 24 electrons. So here's where we're at. I have 4 bonds to place right here, and I have 24 electrons to place. And doing that around the structure should allow me to get octet for all of the atoms involved, and I'll use up all 32 of my valence electrons. The final thing before we can just place everything is to think about the structure. And that's going to happen whether you do the table method or the CCOO method. But we need to find a central atom. Now, sometimes you don't have a central atom. I gave you this example here of hydrogen and fluorine. There's only 2 atoms, so there's no central atom. But in our example here, we've got phosphorus and 4 oxygen. Use common sense. I mean, overall, your central atom is going to typically be the least electronegative, and that was notes from last week. But also, too, if you're thinking common sense, if you have 1 phosphorus and it's listed first, that's going to be your central atom. One other hint, carbon's always your central atom if it's present. It's not present here. So I'm going to go ahead and place phosphorus as my central. And then I'm going to place 4 oxygen around it. And I'm going to try to make that as symmetrical as possible. Okay. So that's going to be my general structure. Now I come back up here and I realize that I need 4 bonds. I'm being told that. You don't have options. If you do the table, you're using 4 bonds. Now you have to assume that you got to 4 bonds correctly. Well, this makes sense. If I'm going to build a molecule, then I'm going to need a single bond to hold all of this together. And it just so happens that uses up all 4 of my bonds, so those are gone. So from here on out, I'm going to be placing electrons as pairs. I've used my 4 bonds. I won't be doing any kind of double or triple covalent bond here. So we will now work from the outside in, and that, whether it's this table method or the CCOO method, you always work from the outside in. I'm going to choose this oxygen over here. I know you can't see where I'm pointing, but notice each of the oxygen, really any of them, only has 1 bond that it's going to be associated with. Remember, that bond has 2 electrons. So for example, here to the right, this bond, you can't really see, but that bond represents 2 electrons. So that oxygen has 2 electrons around it. It wants octet. I need to add 6 more. I'm going to pair them up. So now with a single covalent bond and then 6 other electrons that I've added, that oxygen has octet, has 8 around it, 2 from the bond, and then 6 that it's not going to share. So the only 2 that it's sharing are in the bond. Now remember, I had 24 electrons to place. I'm going to subtract 6 from that. So I've used up 6, and that leaves me with 18 electrons left to go. Now you can see we're going to end up doing that same exact thing for each of the oxygen. So I can come down here. The bottom one's got 2 from the shared. So I need to add 6 more to get total of octet, 8. That takes me down to 12 electrons. We'll do this as well. So again, 2 from the bond, 6 surrounding it, 6 electrons to go. So we'll do it to the top one. And again, that top one now has octet. And I'm out of electrons. And that's okay, but we do need to check one more thing. We're building from the outside in. So I need to check that central atom. Does phosphorus have access to a valence or 8 valence electrons? And it does. Remember, each of these bonds constitutes 2 electrons. So if you think about each of those having 2 electrons to make that single covalent bond, then phosphorus does have octet around it. So to finish this up, everyone's happy. We've used up all of the electrons and bonds it's supposed to, according to the table. And everyone, all the atoms have octet. The last thing we need to do, though, is remember how important that charge was, the 3- charge. So whenever you have, and let me just erase a little bit of this. But whenever you have a situation where you've added electrons because of a charge, you need to show that, and we're going to show that with brackets. So we put the entire structure in brackets, and we put a 3- charge on the outside. So again, there's a nice slow example, took my time, of how to do the table method for something that has a charge. Now, I'm going to move and do one more example, and for this one, I'm going to do the other method. So we're going to reset. So again, this one, the method, I don't know really kind of the proper way to it's CCOO with perhaps a fifth step. And for this one, I'm going to do SO3. So notice we don't have a charge on this one, so I'm not going to need brackets with a charge on it. Now CCOO, the first C stands for count. And just like in the table, at some point, I mean, fundamentally, the first thing you should always do if you don't know where to start, count up valence electrons. So here, if I'm counting up my valence electrons, sulfur, here, there's just one of them. It's going to provide 6. And then oxygen, there's 3 of them. But again, it's also going to provide 6 valence electrons. And so 6 times the 3, we get 18. And so ultimately for the valence electrons, 6 plus 18, I'm going to deal with 24 electrons. So I got to use 24 electrons. Now, different from the table, we're not going to try to figure out how many bonds to use yet. Okay, so just 24 electrons. They'll be paired up, so I don't have an odd number. And so that is good. It doesn't seem like I made any mistakes there. The second C stands for connect. Here we need to figure out what's the central atom. So again, when I look at SO3, I don't see carbon, so we can't make that the central atom. But if I have if I have a sulfur and then 3 oxygen, we need symmetry. And so when I think about this structure, it makes the most sense to put sulfur in the middle. And then the 3 other oxygen around it, and again, try to make it as symmetrical as possible. And remember, we need to connect. So we know sulfurs are central, but I need to actually connect those. So as I'm showing you right now, that's not a molecule. So I need at least a single covalent bond to hold this all together. Now remember, we had 24 valence electrons to work with. But now I know that -6 of those are going to be in the bond. So again, each bond holds 2. I've placed 3 bonds to hold this thing together. And I've now got 18 electrons left to work with. Okay, I'm going to move over here. So the CC, now the O, the first O is octet, but for the outside atoms, not the central. Now I've got 18 electrons to place. The outside atoms in this case are oxygen or oxygens. And as I look, I need to get each of those oxygens with an octet. And so just like in the previous example, and you'll get used to seeing this, I've got 1 bond that each of those oxygen have access to. So that gives them 2 valence electrons in their outermost, because again, they're going to be overlapping and sharing 2 electrons. They need 6 more. So I'm going to go ahead and put 6 more around this one. Now that has octet. It's got 6 that is not sharing. It's got the 1 that it is sharing for a total of the octet. And we had 18 electrons. And by using 6 there, I'm down to 12 electrons to go. We're going to do the same thing down here. And notice I'm pairing them. You have to pair them. So 2 shared in the bond, 6 around the outside not being shared. That total is going to be the octet. But again, I just added 6 more electrons. So now I'm left with 6 to go. And we'll do that one more time. Notice I'm ignoring the central atom. So at this point, we're just focused on the outside octet. And again, I've added 6 valence electrons to that oxygen on the left. And the 6 plus the 2 in the shared bond, we've got octet. I am now out of electrons. So that's something to keep an eye on. CCO, the fourth O, or the second O, but the 4th step is octet. But this time we'll worry about the central. Always leave the central to last. So the central atom is sulfur. Sulfur wants 8 and wants an octet just like everyone else. If you take a look at sulfur, it's got 1, 2, 3 bonds around it, and that's it. Each bond has 2 electrons. So sulfur only has 6 electrons, which is not good. That makes us sad because everything wants octet. So we're not done. This does not work. Okay, this as shown would not exist in nature because that sulfur doesn't have an octet, and it's going to find a way to have an octet. So the way it can have an octet, can't add any more electrons. Okay, so again, we only have 6. We cannot add any more because we've used up the original 24. But what we can do is take one of the pairs that isn't being shared and make it be shared. So let me erase, but and you can choose any. Again, this is something called resonance that we are ignoring for this year, just to try to make things a little bit easier. I'm going to go on the left-hand side, and I don't know, we might be mirrored here. I think we'll be okay. I'm going to choose this pair on the very outside. Now, I don't want to completely lose them. I need to maintain the 24 electrons, but instead of having them not be shared, I'm going to take those two and turn them into a single bond. So notice now I've created a double covalent bond. And remember that each of those lines represents 2 electrons being shared. So this, let me change colors. All right, so let me see if I can somehow draw this. That oxygen's fine. That was never an issue. It's still got its octet. And this oxygen is fine as well. We didn't change anything about those. Whoops. Now let's take a look at this oxygen. And so for this oxygen, you'll notice that now it's got 1, 2 electrons coming from this bond, 1, 2 electrons coming from this bond, and then it's got 5, 6, 7, 8. So that oxygen does now have octet. Keep doing that. And then finally, let's look at sulfur in the middle. It's got 1, 2, 3, 4 from that bond, 5, 6, 7, 8. So it's got octet as well. So we've used up all 24 electrons that we were supposed to. We can't add more. We can't have any left over. And we have all the atoms have an octet. So you're done. And that's the way always to check, is look at each atom does have an octet and make sure you've used up all of the electrons you were supposed to. So originally we were supposed to use 24 electrons, and we did, and we have an octet for all of the atoms present. We don't need to worry about brackets and a charge because there was not a charge originally. And the last thing I'll mention about this one, you can place that double bond on the bottom or on the right or on the left like I did, and it's all correct. You have an option there and that you are allowed to do that. So again, I'm hoping, I know that was probably a bit long, but I'm hoping that going through one more example or a couple more examples helps. Like I said, there's no correct way to approach this, but I would really like you to use one of the methods I've given you, at least to start. And if you get really good at this and you have your own way of doing it, then of course, do it your own way as long as you're getting the correct answer. So hopefully this helps. If not, again, contact me and let me know. I will try to make myself as available as possible on this. And we're only asking you to do part of the worksheet, but you can do that. I've got a key for that entire worksheet. So doing a few more of those here and there is certainly going to be good practice for you. So again, good luck. Let me know what I can do to help.